do professor Jorge Dias, que infelizmente não pôde estar aqui presencial com a gente na data de hoje. Inclusive a gente tinha passagens compradas e tudo, tivemos um problema, ele está remoto para nos apresentar hoje. Então, professor Jorge Dias, doutor em Engenharia Elétrica pela Universidade de Coimbra e atualmente professor na Khalifa University, em Abu Dhabi, no Emirados Árabes. Ao longo de sua carreira aí, trabalhou com robótica, inteligência artificial, percepção, tendo contribuições bastante interessantes na área de fusão sensorial. Trabalhando com fusão sensorial, tanto a parte visual inercial, quanto a parte visual auditiva também. Desenvolveu vários trabalhos na área de robótica probabilística. E, além dessa posição que ele ocupa hoje na Universidade de Abu Dhabi, ele foi professor titular da Universidade de Coimbra, Departamento de Engenharia Elétrica e Computadores, até setembro de 2024. Durante esse tempo, além do trabalho de pesquisa e investigação que ele fazia na Universidade de Coimbra, também foi vice-presidente do Instituto Pedro Nunes, que tem lá em Coimbra, que é focado na parte de inovação, sendo por bastante tempo aí o fundador do Laboratório de Sistemas e Automação do Instituto Pedro Nunes, focado em inovação para a indústria. Ao longo da carreira, o Jorge Dias trabalhou, desenvolveu aí diversos projetos, como PI, de projetos internacionais, tanto na Europa, mais recentemente no Oriente Médio, na área de robótica autônoma e percepção artificial. Então é com enorme prazer aí que eu dou as boas-vindas ao professor Jorge Dias e passo a palavra para ele aqui para a gente poder assistir a palestra Robótica e Inteligência Artificial na borda, como a gente chama no Brasil, Towards Efficient, Intelligent and Autonomous Systems. Professor Jorge, está contigo a palavra. Obrigado.
Muito obrigado, muito bom dia a todos. É com muito prazer que recebi o convite do Paulo Drews e é com muito prazer também que faço esta palestra. E eu vou passar em inglês, não porque não seja possível, mas fico com a dúvida se o meu português consegue ser tão inteligível como o meu inglês. So today I'm just starting sharing with you part of the subject that is quite important for everybody nowadays, doing some kind of activities about the use of new algorithms and artificial intelligence on the Khalifa University. So for the people that don't know too much about the area, let me just tell you that we have many Brazilians here by the chance, but a part of this, the Emirates are a set of federated countries, small ones that some of them maybe know internationally, like the Emirates of Dubai, the Emirates of Abu Dhabi, the Emirates of Ras Al Khaimah, and many others. So in total, 7 of them that are part of the things that are, supported by different universities, and Khalifa University is one university that the government of Abu Dhabi started to just nurturing the local talent. 80% of the students that we have are elite students from the Emirates, normally very top students that can do also courses outside, but they prefer to be aligned with research and education in the country. So this university, along the last 10 years, that a little more than 10 years that I'm there, we started on the time that we arrived to set up a robotics center that is named Autonomous Robotics Center for the moment. We have different kinds of facilities, different labs. We concentrate our activities in different domains that are, until the moment, correlated with the vehicles itself. So we have labs for aerial vehicles, we have labs for land, where we work with driverless cars. We have also labs that are dedicated to things that are related with underwater. The areas that we deal with is multidisciplinary. We mainly focusing on the application side because are very important for us in Abu Dhabi to translate the technology for real problems. However, we have expertise in different domains. We have people that are theoretically very robust on the EI part. We have also people that are specialized in certain technologies, actuators and sensors, soft robotics, and also energy side that we use on the robots. But actually, we are mainly interested in prototyping new devices, and this is what we have been doing long the time. This is just an overview what we are doing, and of course, please put attention on the place that currently is a little more, let's say, with situation that we think that will be solved, very soon. But we definitely like to serve the world, and you can think on the Abu Dhabi as a place for your visit or your stay, research stay. So this is an important aspect. My talk will be concentrated in something that is quite important for the moment. That is how we can put the techniques that we have in machine learning in such a way that we can be very effective on the use of these techniques that are very, very, very good on the results they do on board, that typically push us to have lower consumption and high performance. And what we can see it typically is that nowadays the way we just see the robotics, we have different areas where this kind of type of algorithms are appearing, with lots of algorithms that mainly using machine learning techniques that are using based on the data that you acquire on different domains. One of them definitely is the decision part here, what we call it artificial intelligence, or also on the perception side, that is an area where you pick up the observation from the world and where you maybe infer things that are important for your decisions and the equation in the world. What we are looking for very currently is that we have many data that we got from the sensors. And one of the things that we see is that this quantity of data can be giving good support for these machine learning techniques that you use nowadays, and many of them coming like very intense on certain kind of computing. And this is push to us to have a look on this problem. And one of the things that we see it more currently is that many of the techniques that used on artificial intelligence and machine learning tools are embedded in one principle, that is imitating what we call it neurons, or that you call it neural networks in some cases. And what I try to advocate here in our talk is that we need to have a look clearly what is going on the computing part of these neural networks. Everybody that is using these techniques are really giving a hard time with different kind of hardwares that we can use for speed up and making these algorithms effective. And many of these things are putting a big problem on the edge computing that we need to have on the devices. And this is push us to have alternative ways of thinking, and I will just promote today the use of the spiking neural networks that are another type of computing that you should put attention for the future by obvious reasons that I will explain. First of all, I'd like just to emphasize the following. When we have this kind of artificial neurons that you have nowadays, if you look for the part that are related with computing, what we see is that the neuron is no more than just aggregation of sums of multiplications by inputs that are here on the inputs of the neuron part. So typically the neuron is made by different axons that you have, and these inputs that imitate as axons are they are just pull it with some kind of weighting mechanism to a place where we do the sum of these multiplications. This is basically the transfer function that we have when we have an artificial neural network that currently you associated by different layers and give it different connections, trying to imitate the similar way as we have in the brain. We have neural connections, but what is coming as a fact is that the aggregation of this kind of parts that we have with different neurons are just pushing to the concept that many computations we should do by the fact of you are using different kind of layers. So these layers push the computation part very heavily, and of course we have very interesting mechanism to do the training of these weights that you have, and we know some interesting algorithms. Maybe some of you are just presenting on the conference that we can just fine-tuning these weights, and also how do you define the thresholds for good answers to the inference aspect of these neural networks. This kind of principle that is really important point of view of artificial network is putting us with big dilemma. That is, when we use these neural networks as we do it nowadays, we are really accumulating a lot of sums and a lot of multiplications. From the computing perspective, and you're just looking for this perspective, if you aggregate many of these artificial neurons, we have a bunch or a rig net of weighted sums. This is what is the computing aspect that's come. Of course, the outcomes are quite interesting nowadays, and more with these techniques, we call it by deep learning, where we extend different architectures of connections, and we arrive to the interesting mechanisms to detect, to infer, or really to have some kind of high precision, much better than you had before. In fact, this kind of way of doing it is coming with some kind of engineering that are really known by the artificial intelligence people that are just training using big data that you use for design the networks and training the networks and testing the networks using this data. So there are two main problems when you see here from the computing part. You have the part that we have the data that is accumulated, and it should be big data and very large quantity of data that you can manipulate and use to fine-tuning your weights and mainly do a very good inference. How we do it nowadays is basically exploring very much the use of hardwares that are typically very suitable for multiplication and additions all at the same time. This is what happens with the GPUs that we know, the game area. By the way, they use on the graphics the extremely use of the computations with like multiplication and additions, make these kind of accelerators very good candidates our perspective to use with neural networks. And this is what the people is using nowadays, trying to adapt this kind of GPUs in different kind of stacks of hardware that we have. So basically, nowadays what we explore intensively is these algorithms that we're trying to adapt to with our kind of way of computing and developing softwares using this stack mechanism that you can see it here, that are based on layers of softwares that are interacting and interfacing with each other. And when it comes to the hardware side, typically interface with the operating system and the hardware platform, and use this kind of technique that is quite well known and quite very popular nowadays for developing systems, to use in specific algorithms that are extremely demanding on this kind of parts of computing using additions and multiplications. So what is the problem of this? The problem of this is that typically when you have this kind of additions and multiplications from the computing part, these kind of operations are the most intensive ones on the use of the electronics. You need to do the consumption of much more energy when you do very large amount of additions and also multiplications. And more than that, because the machines that we have are mainly based on the transfer of data between the internal central units and also the memory, the transfer of this memory and also the principal unit that we have, this what we call CPUs, and is putting us very large challenges what we should do it with the consumption of energy on these transfers, the consumption of energy when you do the processing of this data, and also, of course, the use of big quantity of memory. So what we see nowadays is that all this kind of pushing for this type of operations increases very much the quantity of the energy, and as engineers on the area of computing, that mainly is what we use typically on robots, is you use intensively computing. It put the challenge of using these algorithms on small devices that you need to really pay attention how we can link and use these powerful algorithms that are based on the neural networks, artificial neural networks. And this is really a problem that we attend nowadays, where we see the use of artificial intelligence that is mainly based on this neural networks mechanism, and basically we see more and more consumption on the use of this energy consumption on the electronics. So if you're looking for the perspective of autonomous systems, this put a big challenge. Of course, the area of the electronics have a good solution for the, let's say, the low or the computing on the edge, because sometimes and very often the computing of the edge is reduced to the minimum, and maybe just using or exploring big data centers outside of your device to consume and use computing power that is not resident inside of the device that you have. Of course, this works well when you have a mobile device like you have on your mobile phone, because you are always linked to the the internet, and you just use the internet to access big data outside, but make the solutions of autonomous systems a little more curious. In fact, what happens is that we can arrive to the situation situation that if you don't pay attention to how we do the consumption of this energy, sooner or later, these autonomous systems will have all the energy consumed by them to be spread and distributed on the outside of the vehicle itself. You could imagine that you don't spend anymore the gasoline in your car, but you consume the energy outside used by the computing on these big centers that are just doing the computation for the car itself. So this situation is not suitable for really autonomous vehicles. We should think about alternative ways of doing it. And the best way to think about this thing sometimes is really rely on what we call it, inspire ourselves on the nature side. So we have beautiful things that we have in the nature side. We know that from the robotics point of view, many of the creations that you have on the robotics, like here, soft robotics devices that you can do similar has a biological system. You can also think on the way you just see or perceive the world around you by imitating the case like the eyes of this fly, or you can imagine better ways of flying by based on imitating the animals or some kind of morphologies that you can find in animals. So why not think in the same way when you are talking about computing? If you observe what happens inside of our brain, and in fact in our brain we have a beautiful machine that everybody of us typically use it for reasoning and make the correct decisions and acting in the world. And you should really pay attention how this kind of things operate. And in fact, if you look for the situation that you have nowadays on the consumption of power, and if you use the neural networks, many things that you are doing are really dealing with consumption that really are quite heavy if you still associate with insisting on using these neural networks, implementing the neural networks by the principle of additions and multiplications. So what are the solutions that are currently persons like us can think about? Is using and exploring what is in the brain. What is in the brain? We use mainly spiking, like Dirac impulses that happen on the neurons, and these neurons are associated some kind of processing based on this kind of spiking mechanism where the information flows along the brain by aggregations or links by distributing the spikes in different ways. And there are benefits of using this kind of spikes. The energy is just some kind of impulse that you do it. If you do it, you can modulate the amplitude of the impulse, or you can also think on the different kind of interval between impulses to aggregate to the information that you like to transmit. So instead of using parallel beats, we are using the kind of spiking mechanisms that you can use for transmitting the information. This is a new paradigm. This is a kind of paradigm that we call it typically the name in the area of computing, neuromorphic computing. And the neuromorphic computing itself are divided into different parts. And the first one that is quite well known among us mainly is the neuromorphic sensing aspect, that we have typically sensors that are responding to spikes and picking up the information that you got from the data from the sensor, and you just looking for specific signals or features on the data. Typically we have currently a very popular sensor that we do it. We call it these event cameras that are a neuromorphic sensing, or you can use the computing that is really based on spiking, that is neuromorphic computing. That you know, some of the parts that we have, you can imagine that are centralized or distributed in the memory itself. You can also thinking on the different way of doing this neuromorphic computing by distributing on the memory this computing that we call it in-memory computing. So why these techniques are really important? Because what happened nowadays on the classical way, the classic Neumann architecture that is quite popular among us, that become more and more popular by the electronics that's supported by the CMOS and the CPU's mechanisms and the GPUs more recently. We are just dedicating, but currently we have facing the problem, the quantity of the areas that you can integrate in per let's say millimeter are really difficult and difficult to cope with barriers that we have, with the barriers that we are feeling currently for the computing and the actual technologies is that it is really strong in some situations. We know situations we can work also with the dissipation of this energy, of course, are clever ways of doing. To have also the problem of the quantity of memory that you can put in certain areas. Of course, we have also good solutions, but these solutions only jump on the collide with what we call it Moore law. That is the quantity of the limit of that is a constant limit that we have for the derivative of introducing the more let's say electronics by square meter or like a millimeter square. Now this is things make us thinking on this very seriously about this neuromorphic computing. Let's start by looking at what this sensing mechanism has. There are really the one very popular sensor that you have, this neuromorphic sensor, that you don't do more than just collecting images as normal. But what is resisted by the sensor is not really the illumination or the quantity of energy that comes to you, but no more than just the derivative of the change that you feel it. So this kind of event camera are really related with the dynamics that you see it on the image, and you recover from the image not absolute values of the radiance, but you just pick up what is the derivative of the signal itself. This is really decreased a lot the quantity of data that you have. So when you use neuromorphic sensing in that respect, also the event cameras, the quantity of data that you need to process is much less than the normal image cameras that we have. Of course, we don't understand sometimes the existence of these small dots that you see it here, but in fact these small dots are just irrelevant very often, because this sensor can really be giving to everybody very interesting results. And this is the first image in the left that I put it here, is the image normal coming from a camera, where the camera are observing a scene, and the scene is very important to understand the scene, where are the illumination. The illumination, so you can see parts that are totally black on this first part of the scene. However, when you come to the part that are less illuminated, you cannot see what is inside. However, if you associate the event cameras doing a superimposing mechanism, when you see the illumination on the dark part, what you arrive to the conclusion is that automatically you can start seeing things that you don't see it typically with the normal camera. You can start seeing, for example, better during the night, and actually is what you have done on some work that we have really do tests with off-road on the desert on the Abu Dhabi with our group. This is an image in the night where the person with the camera are trying to involve along the path on the sand, but it's very difficult to distinguish what is going on because you cannot understand what is happening on the scene. However, if you put the same scene with event cameras, it's totally different story. We can really see what is happening. Let me just put a little more time here on the scenario here, a little more constant, and you can really distinguish the road much better than when we superimpose the event cameras. So what happens here is that this event camera by itself give the picture that you need to do the navigation. This is just one effect that is extremely important, and you don't need to accumulate all the data that you got from the image itself. In fact, you have a mechanism of compressing the data itself. So the neuromorphic sensing typically do these two effects, is compressing the information and also give the pictures that you like to use, and you should be clever on the use of this neuromorphic sensing mechanism. This is opened the door for different paradigms of computing, different ways of implementing algorithms, and you should pay attention a little more and on the use of this kind of neuromorphic sensing, especially with event cameras. There are many of colleagues on the area exploring these event cameras, and I think you should put more attention on another areas that we can use. Typically in Abu Dhabi, in the group, we are currently looking for mechanisms of grasping, and we can compute the grasping mechanism in the different ways, where we don't measure the sensation of the grasping by typical forces like with transducers that are related with the force itself, but you use the event cameras to detect differences on this kind of places where you see the displacements. And this is interesting work. You may pay attention and have a look. Another important aspect I need to emphasize is that we really can and we should do a little much more on the in-memory computing. The in-memory computing, the limit is no more that the functions that you like to compute pre-loaded in the memory. So you don't need to do any computation. You use just extensively the memory, and we have these lookup tables where the results are hashed and cached automatically when you do the computing. And this is kind of a more simple case. However, this simple case have a strong benefits because when you do the in-memory computing directly, many of the things don't needs to be done. The bottleneck that you have for do the function that you would like to compute, you don't need to put in the CPU and retrieve back the result from the CPU. This fetching and the major bottleneck on the transmission of the data between the memory itself and the CPU should be just removed directly by the in-memory computing. Everything is in the memory. What happens is the CPU itself find the values of the function directly by the access correctly the lookup tables that you have inside of the your memory that is in memory. We call it in-memory computing. This paradigm is normally not used directly by the language that you use, this when you use C++ or Python, or this kind of concept is not easy. You need to program it yourself, and also when you program it yourself, you need to be careful, because when you do this kind of computation, when we do access to memory, we make the transfer anyway. Okay, so what happens with the in-memory computing, you just remove the bottleneck of the fetching and putting the result in the memory after the computing by the CPU. This is a really important thing, and very recently we have simulators done on our system on chip lab, that we trying to simulate what we call it memristors. That is a different kind of material where we can adapt these weights of these, the outputs of the memristors are really imitating by in-memory access as a neural network. And is very interesting, the mechanism and what you can save and energy and time by doing that. Today, I don't concentrate on these two kind of sensing or in-memory computing, but mainly on the neuromorphic computing. That is a different aspect that nowadays we are not just alone on this kind of community. We are just have big players also looking for this aspect, and this is our work is mainly related with this kind of processor that are related with Intel, that use this LOI, that is one kind of spiking mechanism for transmitting and computing. What is this principle? Is that what we are trying to do is mainly distribute the principle of spiking, and playing sometimes with the length of the time scale, sometimes with the amplitude of the spiking. There are these two approaches for doing this, the spiking neural network, but definitely one benefit that you may understand immediately is by the fact that when you have a spiking mechanisms, multiplications like this one, spiking like the multiplication is the quantity of spikes that you do. The quantity of spikes that you generate are proportional to the multiplication that you are generating. If you have, for in this case, a multiplication that the weight is a little bit higher, we have more spikes. The multiplication is the value is different, you have less spikes. And the spikes are really, you can manipulate the quantity by the time or by the inference or the amplitude. You can also use the amplitude. And one interesting aspect that comes immediately by this effect is that the sum itself is just aggregation of common pulses. When you aggregate a train of beats or a train of impulses, you just sum them along the time. You just need to synchronize them on the time, and then you don't need to do the addition itself. So the things that happen this way is quite interesting, because you don't need really do the sums. You don't need neither to have another mechanism that's just spiking. Of course, you can say you lose some time on the parallelization, because when you do the sum by parallel way, maybe you save some time. However, because you need to do the multiplication operation, you take more time than just serialization of the data. So you need to do serialization of the data. Of course, it takes time. However, this is much more efficient than you just do the sums and the multiplication, and the time consuming to them is just much more abusive than anything else. And the situation of fusion, for example, where we have two kind of fusion mechanisms or two inputs, are really very easy, and you can aggregate different kind of neurons very easily. You don't need to have, some kind of synchronization of data where you have clocks that are similar, this latch mechanism that some of you maybe know about it. And the threshold that you define maybe also fires the lexon or the neuron itself, depending the way you adjust the threshold. You can make it by electronically, and you have also situation that you can be dynamically and adaptively do it. And actually, the SNMs that you are using, you adaptively adjust you have a technique that you adjust this kind of thresholding adaptive by the training itself. So you don't need to do much more than we have done in the past, but in fact, saving time and also mechanisms a little different for the learning process. So we have, in fact, we can explore this for techniques as classification or object recognition that you know very well on the area. And actually, what happens is that with this spiking neural network is no more than the same kind of architectures that you have for neural networks. However, but the information that you aggregate there are based on spikes and the mechanisms of spikes. And everything that you do with the techniques of using CNNs or convolution mechanisms or transformers should be adapted to this kind of spiking neural networks. And this is just one example, very well displayed by the Intel, where you have the consumption of energy when you try to do an operation similar that we have here. Here is results of our work on the de-aging of water, where you try to recover the good appearance to the water in the right side. And this is just one kind of hashing based on the learning mechanism that you have is in these neural networks implementing with spikes. When you do it in different kind of implementation, like using the algorithm, but using the CPU or using GPU or using the Jetson together with some kind of fasting caching or another type of software hardware that is Movidius or LOI, the difference is quite huge when you use the GPU. The GPU consumes much more energy than anything else, than also the CPU itself. So you need to be careful on the use of these algorithms. This is the first, let's say, message that they like to tell it to you, and you should be clever on the way you just do this kind of serialization of this kind of extensively use of the CNNs, convolution neural networks, that increase the problem of energy very much. In California University, we are strongly dedicated to do this kind of activities, mainly because we have different kind of devices. Nowadays, the architecture that we are trying is you explore what we can explore on the sensing part. We are mainly concentrated on the use of event cameras, not too much on the new transducers for the neuromorphic sensing. However, for the robomorphic computing or neuromorphic computing, we strongly rely on SNNs and also optimizing, these neural networks for the spiking way of representing, the architectures. We have first tentative for the decision aspects. That is the future work that you just put aside to you with kind of activities that we have for looking navigation and other aspects. This is one of the words that we use for the spiking mechanism using CNNs. Again, you can see here situations where we have different kind of algorithms here. And the kind of mechanisms that we use for the energy that you are consuming is really quite huge when you use the typical pipeline mechanism that you don't explore the SNNs. We have some work also on the transformer side that is a little more complex. We have some kind of feedback that you apply, and mainly what we develop in this transformer is really the threshold that I mentioned to you, firing the neurons in a certain way where these alpha are are adjusted according to kind of learning that you have, and you optimize it according to the training sets that we have. And this is the case that we use for the asing. So the previous one, we don't use any kind of adaptive mechanism on the spiking neural networks. Here we use the transformers for the spiking mechanism. This spiking transformer that it was somehow developed by us, and we explored it intensively for the same algorithm, like recover a very good images. And this is the examples of this mechanisms of operating on these different images. So this is something quite important. And when you looking for the ratio of energy, for example, the ratio that you got it for the SNNs are really low, and when you do some kind of algorithms that explore partially use of no adaptivity, but using also SNMs, you don't the adaptivity using transformers are increasing very much. The energy become very low, and so the performance become very very nice to see it. So there are two aspects on the use of this kind of spiking neural networks, is that we can also have algorithms that are very efficient on the convolutional networks to be adapted to the situations where we have also this kind of algorithm running with the spiking neural networks. It's not just the information based on spiking, but actually we can also develop algorithms that become very specific to the use of the spiking mechanism. This is really important. If you is and relevant, if you are interested to see it, you can just have a look on the publications that you have in the area that are really interesting for us in some respect. Okay, so I'm just have stuck somehow here. What is interesting to say is that, there are one interesting mechanism that we like to emphasize, is that when we train the neural networks, and if you train based on the SNNs, what comes across is that the energy by itself, a part of being less consuming on the inference, the effect of learning and improving the threshold really make a big decrease of the energy that you consume. So for the same neural network, without changing anything, using the same neural network, without just nothing more than just training better, what we arrive to the conclusion is that with this table here is that we can really improve by different kind of learning mechanisms and using the CNNs, increase a lot the energy consumption become a little better and less energy consumption. So this means that it is very easy to have a mechanism of optimizing the spiking neural network, and when you optimize the spiking neural network, the optimization is not as normal when you do the optimization for a convolutional neural network where you pruning and you remove data. What is happening is that the same network is the same, however, the quantity of firing and the neurons that are fired are less in certain situations, and by this effect, automatically by the learning mechanism, this happen, and you don't need to really do too much more than just training well your neural network. So you don't need to go to techniques that we know very well from the convolutional neural networks, like pruning or really remove the quantity of data that you have just to make a correct inference without use all the big data that normally you have the trend to use in generalize it convolutional networks or systems that use intensively deep learning techniques. So this is an important aspect, and this is really something that I'd like to emphasize. So the spikel neural network, by default, when you train, the trend is to consume less if the way you train is coming like a very good performance. You arrive to the performance and you consume less energy automatically. So you don't need to have another technique in the middle. So this is one interesting aspect that I'd like to emphasize to you. And here is a case where we use this neuromorphic way of computing, but now with two different kind of signals. One is the images, and another one is inertial data, and you try to combine both to have, a post-estimation on the device, on the camera itself, is what we call a visual inertial computation, where we have the pose of the device that is capturing the data, that in this case is a robot, and to have the pose itself. One interesting thing to mention on this is the baseline that we have nowadays for these techniques is quite good. We have keeping a drift rate quite also good, but the energy that they consume is on this value, and the quantity of operations that you do is about this number here, that is in giga operations. When you arrive to situations that you use the fixed threshold or adaptive threshold, what is interesting is that you maybe keep the same kind of operations the typical similar way. However, the energy that the quantity, but the operations are different, but you can assume that is a kind of operations, and the number by itself. But the energy that you got it is totally different way. So if you looking for the architecture they have here, the operations occur, but the energy that are involved on this are really smaller because the number of spikes are completely different. Then you have really a good performance when you come to the energy side. So one of the things that I'd like to maybe pass here is our this video that shows a little more about the work that we have. We call it Neuron VIO. This is a hybrid neural network. That part of the neural network is CNNs, another part is also using spiking, using this transformer side, and for multimodal post-estimation. So